go through a few examples. And strontium's not the only game in town. The other sort of long-lived isotope systems that we have of interest, some of them are given here, and they all have individual values of lambda depending upon the isotope we're looking at. So lambda is different depending on which radioactive isotope it is. So this is the parent isotope. This is the way it decays, either by beta decay or electron capture or alpha decay. This is the value of lambda for that isotope with its half-life. This is the daughter isotope. Actually, you'll see for the top one, potassium-40, actually produces both argon-40 and some calcium-40. It's called a branch decay. But actually, it turns out that decay to calcium-40 is fairly minor. It's not very important. We don't need to worry about it. We're most interested in the decay to argon-40. In that case, our reference isotope is argon-36, since it's not radioactive, not produced by radioactive decay. And then we can go through all the various other isotopes. And they all follow exactly the same principle. So let's look at an example of a rubidium-strontium system. So this is the Sudbury intrusive in Canada, which is associated with the world's largest nickel deposit. And it's quite old, and it's thought to have formed when a meteorite hit the Precambrian shield in Canada, and it punched a hole through to the mantle, and it allowed nickel-rich melts to come up from the mantle and form this massive nickel deposit. And it's huge, and it supplies a huge proportion of the world's nickel. And so there's been a lot of study on it, and one of the interests is obviously in dating it. How old is this deposit? So in this case, a dozen samples were taken from this intrusive complex, and the strontium isotope ratios were measured, and the rubidium strontium ratios were measured in each sample. These strontium isotope ratios are given 5 figures here. We can measure them to a precision of 1 in this final figure. So we can measure them extremely precisely. Okay, so what we do then is we put a line through those. That's our isochron. The intercept of that line, 0.70733, that's our initial strontium isotope ratio. The slope, 0.02582. So we can solve that slope and for t, and so t is natural log of slope plus 1, and not natural log of that, and divide by lambda, the decay constant, gives us our age. Okay, a few things to get from this. First of all, although the data define pretty good straight lines, it's not perfect. Some of those dots are a little bit above the line, some are a little bit below the line. This is an old rock. This is 1.8 billion years old. So, things may have happened. It may have been slightly metamorphosed, there may have been some slight weathering, there may have been some fluids that may have passed through that rock and changed things a little bit. Nevertheless, it's a pretty good fit. But you'll never get an absolutely perfect fit. What else can we see from this? Well, another thing about, okay, so you do this calculation in your calculator, and you get this number here. And there are 10 digits here. So, you write down 10 digits as your answer. I've just told you, actually, we can measure to 1 in 5 digits here, and that's doing really well. That's a really precise measurement. So there is no way we would quote our final answer to 10 figures. Probably 4 is about the best we can do, because that actually is the limit of measuring the rubidium strontium ratio. So significant figures are important, because the number of significant figures you quote in an answer tells your reader how precisely you think you know that answer. And you do not know that answer for the last final year. Okay, the other thing is, okay, if you just put down this number, well, I'd defy you at first looking at that to think whether that's sort of 17 billion, 17 million, or, too many numbers. So when you've got a very big or very small number, always write it in scientific notation, times 10 to the power of something. You'll also see this written very often for ages. So GA, giga stands for giga years, or 10 to the 9 years. MA, million years. KA, 1,000 years. Okay, so let's have a look at these other isotopes here then. Potassium-40 decaying to argon-40. Well, argon is a noble gas, sits on the right-hand side of the periodic table. As I mentioned in the first lectures, noble gases don't bond to anything. So argon doesn't really want to be in a mineral. It's not bonded to anything else in the mineral, so when you form argon, form radioactive decay of potassium, it's kind of rattling around in this mineral cage. And if you heat up that mineral a little bit, you sort of expand the bars in the cage, so to speak, and the argon can escape. So the potassium-argon radioactive clock is very easily reset by relatively low-grade metamorphism. Decay of rubidium to strontium, well, that's actually pretty good, bog standard decay way of dating igneous rocks, and it's good as well because rubidium and strontium have quite different geochemical properties, so there's quite a range of rubidium-strontium ratios in different minerals, and that helps us with our dating. But rubidium is, it's reasonably mobile, so if you heat a rock up to 400 degrees or so, you can start to get diffusion of rubidium, and you can reset that clock without actually melting the rock itself. Decay of samarium to neodymium. Well, samarium and neodymium are both rare earth elements, sit at the bottom of the periodic table there, and they've got very similar geochemical properties. So that means that actually the samarium-neodymium ratio doesn't vary a huge amount between different minerals, and obviously if all minerals had identical samarium-neodymium ratios, well, it wouldn't work for radioactive dating. There is a small spread, and it's big enough for us to use. The big advantage of the samarium-neodymium system is that the rare earths are very resistant to metamorphism. So when we form a rock, then provided we don't melt it, we can be pretty sure we're going to get the original age of that rock, even if it's been metamorphosed. So these other isotopes have got more specialist applications, and I'm not going to discuss them in any significant detail, lanthanum, lutetium, rhenium, and uranium isotopes we'll talk a bit more in the next lecture. So, you need to understand the principles of radioactive decay and go through the maths of how I constructed that basic decay equation. You need to be able to understand that, and you then need to be able to understand how we can construct an isochron plot and solve it for H. Okay, so let's see how much you've taken in here then. Right, so let's off. Right, basic decay equation for decay of potassium-40 to argon-40. Okay, you've got the information up there. Right, what are we going to start off with here then? Same way as for strontium, what are we going to start off with? Okay. Come on. Wakey. It's not dark yet. You know, come on, that's enough of a co-star answer.
Wait, which one do we do?
Plug in the equation with the equals below.
No, we can sort of just take the strontium isotope one. We don't need to go quite that far back, but good good if you understand that.
Oh, it's an alpha decay mode, so it'll be SN.
Well, no, we just want to write down the basic decay equation.
Oh,
No, that was the sort of mechanism of radioactive decay. Go on then.
Is it potassium just goes to argon and an electron?
Yeah, but that, okay, remember, okay, let me just quickly shoot back a bit.
plus an electron. Near the electron.
Okay, that's the basic decay equation at the top for strontium. Okay? Right, so now give it to me for potassium. All the information you need is on that top line.
Which case
What?
it'll be
K40 plus electron goes to argon.
Yeah, so you want that the equation we're going to use for constructing an isotop. And we're going to have an XY plot. And for strontium, I had 87 rubidium, 86 strontium, again 87 strontium, 86 strontium. Okay, so I'm going to have something similar for the equation I'm going to need for potassium isotope. Okay, all right, let's start it off then. We're going to, the ratio we measure is argon 40 over argon 36 that we measure today. This is our daughter isotope. This is our reference isotope. That's going to be equal to same thing, yeah. Same thing, but with one slight difference,
Zero.
which is
Zero.
0. Yeah. And what does that mean?
It's been 0 one at a time.
That's what we started with. That's the ratio that our sample started with. Okay, and then
K40.
yeah, potassium 40 over argon 36
brackets
times E, then E to the lambda T minus 1. Okay, so that then is the basic decay equation for potassium 40 decaying to argon 40. Okay, so that took a while, but we got there.
That's what I thought you
Get
wanted
some one line.
these. I thought you wanted this
So
one.
having done that, it should be now very easy
Yeah, what's this?
to do this for the decay of 147 samarium to 143 neodymium. Okay, so we've done it once.
143 rubidium over 144 rubidium.
Yeah, so 143 neodymium that we measure today is equal to
The same again with a 0.
the initial ratio plus
147 SN.
147 samarium divided by 143 neodymium times E lambda T minus 1.
Would it not be 144?
Beg pardon?
Would it not be 144?
Sorry, 144, I beg your pardon. I apologise. Okay, so it's exactly the same format. So you have your, this is our daughter isotope, 143 neodymium. This is our reference isotope, 144 neodymium. This is the ratio we measured today. This is the ratio we start with. This is our parent isotope, 147 samarium. Our reference isotope, 144 neodymium. E to lambda T minus 1. Lambda again depends on the isotope of interest. Okay, there we go. So those are our decay equations. Oops, sorry. Okay, so pretty straightforward. Okay, so for this system, I said argon's a noble gas. So when a mineral first forms, there is essentially 0 argon in that mineral. Because as mentioned, argon doesn't like to form bonds. So there essentially, that initial ratio is going to be 0. How can we then simplify our equation? If that ratio is 0, what can we knock out of that equation which makes life a little bit easier? So this is 0, yeah?
It means you don't have to have the reference, the reference for isotope ratio?
Exactly right. So we can take this one out completely because that's 0. We don't need reference isotope there now. And the equation simply becomes the amount of argon 40 we measure in our rock is equal to the amount of potassium 40 we measure in our rock times E to lambda T minus 1. Becomes much more simple. It's a relatively simple isotope system to use. I mean, it still has its issues, and there are still, some difficulties with using this system, but it, in principle, it's relatively straightforward. Okay, so given that, here we go. This is